Unit 1.13 is all about removing discontinuities, specifically in piecewise functions. We're going to use algebra and the definition of continuity with piecewise functions to determine how to eliminate a removable discontinuity. Oh, and this cat, well, he's saying there's a reason he's here, and there is. You just wait and see. So before we start, let me, in full disclosure, openly admit that I snagged these slides off of the video from AP Classroom. It was just too cute of a way to present this, and I just couldn't resist. So this came right off of College Board's video, and our AP guide presents this slide just like this, and he asks us which one of these statements could not be true. So he asked you to turn off the video. I'll ask you to do that too. Pause it, and then come back and see if you can guess it. Well, the answer is C. What could not be true? Because they're telling you that f of x is continuous on the real numbers, and if so, that means that the limit as x goes to c for any of those numbers must exist. And they're saying here, f does not exist, so that just cannot be true. So then, if we say to ourselves, which of the following is true? Well, if the limit exists and f is continuous, yes, that could work. If f is not continuous, the limit could still exist at x equals 4. If f is not continuous, the limit might not exist at x equals 4. So we really don't know. We need to reveal the function to eliminate the other options. So here's where it gets super cute. The AP guy gets ready to reveal the function. And at the moment of the reveal, the AP guy's cat has its paw on the work that we need to work with, so we can't get anything out of it. So he politely asks his cat, Estelle, if she will please move her paw. And then you get this balloon, no, which is so cat. I've never had a cat, but that's what I hear, so cat. So what does AP guy do? Since she won't remove her paw, AP guy changes the problem. And here's what we're going to work on. We're going to start with this statement. It is known that the limit as x goes to 4 of f of x exists. If that's true, it means that the limit as x goes to 4 from the left of f of x is equal to the limit as x goes to 4 from the right of f of x. So that means if I look at coming from the left, I plug in 4 there, I'd have 4 squared plus k equals, and plug in 4 to the one on the right, negative 3 times 4 plus 18, which means that 16 plus k must equal 18 minus 12, 6. I'm sorry, that's 16 minus k, my bad. Minus. So k has to equal 10. That's how you do this. I think we've done some like this in other stances, but that's how you do the problem, and I just thought it was super cute how he presented it. So let's try one that's similar but not nearly as cute. Okay, you're given this piecewise function, and clearly there's a hole because the function is defined when x equals 6 by another value. So I'm going to find out where that hole is. Well, the hole is occurring because I can factor the expression and then cancel the problematic binomial out of the denominator, so the hole is occurring at x equals 6. At x equals 6, we have a hole, which is a removable discontinuity. You may recall from pre-calc that I want the coordinates of the hole. Well, x is 6. All I do is I plug 6 into the reduced function, which is x plus 3. And that gives me my y value, so y equals 9. So the coordinates of the whole are 6, 9. I don't really need to find that, but there's a correlation, as you'll see. So part B, what is the limit as x approaches 6 of the function? So if we're approaching, we're using the upper function there, where x is not equal to 6, but we're getting close to it. So limit as x approaches 6 of x plus 3. Direct substitution gives us that that's 9. And then what does the a value need in order for the function to be continuous? Well, we know that the limit as x goes to 6 of f of x must equal f of 6. We already figured out that that was 9, and f of 6 is a, so therefore a must equal 9. I definitely thought the cat method was way cuter.